Right now, as you're watching this video, there might be infinite versions of you making slightly different choices in parallel universes, just a quantum breath away. In one universe, you clicked on a different video. In another, you paused to grab coffee. In countless others, the very atoms that make up your body are arranged in ways so similar, yet so different that you would recognize yourself, but not your life. For decades, the greatest minds in physics have proposed that our universe isn't alone. The multiverse theory suggests that reality as we know it is just one bubble in an infinite cosmic foam, where every quantum possibility plays out somewhere, where every decision creates new worlds, and where the fundamental constants of physics take on every possible value across an endless expanse of parallel realities. But here's what makes this genuinely disturbing. If infinite universes exist right alongside ours, containing infinite variations of everything we've ever known, why can't we detect even a single one? This isn't just an academic curiosity. The implications are staggering. We're potentially surrounded by infinite versions of Earth's history, where the dinosaurs never went extinct, where humanity developed along entirely different paths, where the laws of physics themselves operate under different rules. Yet these realities remain completely invisible to us, as if separated by an impenetrable barrier that no technology can breach. Leading physicists from Max Tegmark at MIT to Carroll at Caltech have spent their careers grappling with this paradox. The mathematics supports multiple universe theories with elegant precision. The quantum mechanics we observe daily practically demands that parallel realities exist. String theory requires extra dimensions that could house countless universes. Yet our most sophisticated instruments detect nothing beyond our cosmic horizon. Tonight, we're going to explore one of the most profound mysteries in modern science: why the multiverse hides itself so completely from detection. We'll journey through the strange world of quantum mechanics, where reality splits with every observation. Examine the cosmic evidence that suggests our universe had siblings, and confront the technological and philosophical barriers that keep infinite worlds invisible to us. What we'll discover challenges everything we think we know about reality itself. By the end of this investigation, you'll understand why some scientists believe we're trapped in a cosmic prison of our own making, why others think detection might be fundamentally impossible, and why a few radical thinkers propose that we might actually be detecting other universes right now. We just don't recognize the signals. The story begins with a simple question that leads to anything but simple answers. If infinite realities exist, each containing infinite variations of everything we've ever known, what prevents us from finding evidence of even one? The answer reveals something profound about the nature of existence itself. Something that will change how you think about reality forever. But this isn't just about abstract physics. The multiverse detection problem touches on consciousness, free will, and the very meaning of existence. If all possible versions of your life exist simultaneously across infinite realities, what makes your experience special? If every decision you could ever make plays out somewhere in the vast expanse of parallel worlds, do your choices actually matter? These questions have driven scientists to the edge of what's knowable, forcing them to confront the possibility that some truths about reality might be forever beyond our reach. The multiverse might exist in such a way that detection is not just technically impossible, but logically contradictory, like asking what color the number 7 tastes like. Yet the search continues, driven by tantalizing hints that other realities might leave subtle fingerprints on our own. Quantum experiments reveal behavior that seems to require multiple realities to explain. Cosmological observations show anomalies that might be echoes from parallel universes. And cutting-edge theories suggest that what we interpret as empty space might be teeming with invisible worlds. If you're fascinated by the deepest mysteries of existence and want to explore the boundaries between science and philosophy, subscribe and hit thumbs up. And here is a thought experiment. If you could send a single message to a parallel version of yourself, what would you say? Comment below. I'll pin the most profound answer. The journey we're about to take will challenge your assumptions about reality, consciousness, and the very nature of scientific knowledge. We'll explore why the multiverse might be the ultimate example of something that exists but remains forever undetectable, and what this tells us about the strange cosmos we inhabit. Some discoveries in science expand our world by showing us more of what exists. The multiverse detection problem does something different. It expands our world by showing us the infinite magnitude of what we cannot see, cannot touch, and may never know exists, even though it might surround us completely. This is the story of infinite hidden realities and why they choose to remain hidden. Now let's begin our journey into the invisible cosmos that might contain everything that ever could be, but which keeps its secrets locked away behind barriers we're only beginning to understand. Chapter 1. Hidden Cosmos. The multiverse isn't a modern science fiction fantasy. It is an inevitable consequence of our best understanding of physics. When physicists first realized that quantum mechanics and cosmology might require infinite parallel realities to make mathematical sense, they weren't trying to imagine alternate worlds. They were simply following the evidence where it led, even when it led to the most extraordinary conclusion in scientific history. Consider the cosmic microwave background radiation, the afterglow of the Big Bang that permeates all of space. When NASA's Planck telescope mapped this radiation with unprecedented precision in 2013, it revealed something unexpected. The universe appears remarkably uniform, with tiny fluctuations that match theoretical predictions almost perfectly. But this uniformity itself presents a puzzle known as the horizon problem. Different regions of the observable universe that could never have communicated with each other show identical temperatures to within 0.0001 degrees. This is like finding the two strangers on opposite sides of Earth who have never met or communicated are wearing identical outfits down to the last detail. The probability of this happening by chance is essentially zero. Cosmologist Alan Guth proposed inflation theory in 1980 to solve this puzzle, suggesting that the early universe underwent a period of exponential expansion faster than the speed of light. But inflation theory, when fully developed, doesn't predict just one universe. It predicts eternal inflation, a process that creates infinite bubbles of space-time, each becoming its own universe with potentially different physical laws. The mathematics are compelling. If inflation happened once, it should happen continuously throughout an infinite multiverse. Our universe would be just one bubble in an endless foam of realities, each beginning with its own Big Bang, each evolving according to its own version of physics. Andre Lind at Stanford University has calculated that this process of eternal inflation should produce approximately 1,010,107 observable universe-sized regions every second. That is a number so vast that it exceeds the total number of particles in our observable universe by factors that defy comprehension. Each of these regions could develop into a cosmos as rich and complex as our own. But here's where the story becomes strange. If this theory is correct, then infinite universes are being born every moment, each containing countless worlds, countless civilizations, and countless versions of every possible reality. Yet we detect none of them. They exist beyond a horizon that seems absolutely impermeable to observation. The inflationary multiverse theory makes specific predictions. It suggests that some universes should have slightly different fundamental constants, different strengths of gravity, different masses for particles, different values for the speed of light. Most of these universes would be sterile, unable to form stars, planets, or life. But in the infinite ensemble, some would be remarkably similar to ours. In fact, the theory predicts that exact copies of our observable universe should exist, complete with identical copies of Earth, identical copies of human history, and identical copies of you reading these words right now. The distance to the nearest identical region has been calculated by Max Tegmark, approximately 101,028 meters away. That's unimaginably far, but in an infinite multiverse, such duplicates are not just possible, they're inevitable. Yet this cosmic abundance remains completely invisible to us. The light from these parallel worlds can never reach us because they exist beyond our cosmic horizon. They're not hidden by distance alone, but by the fundamental structure of space-time itself. This invisibility has led some scientists to question whether a multiverse theory is even scientific. If a theory makes predictions that can never be tested, is it still science? Karl Popper argued that untestable theories fall outside the realm of scientific inquiry. But supporters point out that the multiverse isn't proposed as an explanation for what we can't see. It is an inevitable consequence of explaining what we can see. The uniformity of the cosmic microwave background radiation, the flatness of space, the specific values of fundamental constants that allow complex structures to exist, all of these observations point toward inflation theory. And inflation theory, when fully developed, inevitably produces multiple universes. This creates a profound paradox. The very success of our theories in explaining our observable universe requires the existence of infinite observable universes. It's as if the universe is playing a cosmic joke, demanding that we accept the existence of infinite realities while ensuring that we can never confirm this acceptance through direct observation. The implications extend beyond cosmology. If infinite universes exist with slightly different initial conditions, then every possible arrangement of matter and energy that doesn't violate the fundamental laws of physics exists somewhere. This includes universes where you made different life choices, where history unfolded along different paths, where alternative versions of physics allowed for entirely different forms of existence. But these realities remain forever beyond our reach, hidden behind horizons that no technology can cross. We are left with mathematical certainty about their existence, coupled with experimental impossibility of their detection. A combination that challenges the very foundations of how science understands reality. The hidden cosmos that surrounds us might contain infinite treasures of knowledge, infinite variations on every theme we've ever explored, infinite answers to every question we've ever asked. Yet it maintains perfect silence, revealing nothing about its contents, offering no confirmation of its existence beyond the mathematical necessity that brought it into being. This is our first glimpse into why the multiverse detection problem runs so deep. It's not simply a matter of building better telescopes or developing more sensitive instruments. The barrier that separates us from other universes appears to be built into the very fabric of reality itself, making detection not just difficult, but possibly meaningless as a concept. Tomorrow's chapter will explore how quantum mechanics adds another layer to this mystery, suggesting that parallel realities don't just exist in distant space, but might be constantly branching off from our own reality at every quantum event. The hidden cosmos might not just surround us, it might be continuously spawning new versions of itself, including new versions of us in every moment that passes. Chapter 2. Quantum splitting. Every time you flip a coin, quantum mechanics suggests that the universe splits. In one reality, it lands heads. In another, it lands tails. Both outcomes exist in parallel dimensions that diverge at the moment of quantum measurement, creating infinite branches of reality that spawn faster than consciousness can comprehend. This isn't philosophical speculation. It's the many worlds interpretation of quantum mechanics, first proposed by physicist Hugh Everett III in 1957. When properly understood, quantum theory doesn't just allow for parallel universes. It seems to demand them with mathematical rigor that has convinced some of the brightest minds in physics. Consider the famous double-slit experiment, performed countless times since Thomas Young first demonstrated it in 1801. When you fire a single photon at two parallel slits, it somehow passes through both slits simultaneously, creating an interference pattern that proves it traveled multiple paths. But the moment you observe which slit the photon passes through, the interference pattern disappears, and the photon behaves as if it only went through one slit. Traditional quantum mechanics explains this through wave function collapse, the idea that measurement forces quantum particles to choose a definite state from multiple possibilities. But this explanation raises uncomfortable questions. What constitutes a measurement? Why does observation change reality? How does the universe know when someone is watching? The many worlds interpretation offers a radically different explanation. The photon doesn't choose a path, it takes both paths, but in different universes. When you measure which slit it passes through, you don't force the photon to collapse into a single state. Instead, you split reality itself. One version of you observes the photon going through the left slit in one universe, while another version of you observes it going through the right slit in a parallel universe. Physicist David Deutsch at Oxford University has calculated that a single quantum measurement on a photon could create approximately 10,100 parallel universes. These aren't just abstract mathematical constructs. They're full realities, complete with their own versions of every atom in existence, every planet, every star, and every conscious being capable of making observations. But here's what makes this deeply unsettling. If every quantum event splits reality, then the branching happens continuously. Radioactive decay creates new universes every nanosecond. The firing of neurons in your brain spawns parallel realities where your thoughts follow different paths. The collision of cosmic rays with Earth's atmosphere generates countless worlds where history unfolds, according to subtly different quantum events. Sean Carroll at Caltech has estimated that our observable universe contains approximately 1,090 particles. Each particle undergoes quantum interactions billions of times per second. If each interaction spawns new universes, the rate of reality multiplication becomes truly incomprehensible. We're not talking about a few parallel worlds, but about an infinity of infinities, expanding exponentially with every moment that passes. Yet despite this cosmic proliferation of realities, we detect none of our parallel selves. The quantum splitting that creates infinite universes also ensures their complete isolation from each other. Once realities branch, they lose all ability to communicate or influence one another. Each universe becomes a closed system, unaware of its countless siblings. This isolation occurs through a process called quantum decoherence. When quantum systems interact with their environment, they become entangled with an enormous number of particles. This entanglement effectively destroys the quantum interference between different possible states, making it impossible for information to pass between parallel branches of reality. Wojciech Zurek at Los Alamos National Laboratory has shown that decoherence happens incredibly quickly for macroscopic objects. A dust particle in air loses quantum coherence in about y-31 seconds. A human being would decohere in less time than it takes light to cross an atomic nucleus. Once decoherence occurs, parallel universes become as separate as if they existed in completely different dimensions of space. This creates a profound paradox. Quantum mechanics provides our most accurate description of physical reality, predicting experimental results to more than 10 decimal places of precision. Yet its most natural interpretation requires infinite parallel universes that remain forever undetectable. We are forced to accept the existence of infinite realities, while acknowledging that we can never find evidence for any reality except our own. The implications become even more strange when you consider consciousness. If every quantum event in your brain creates parallel universes, then every thought you've ever had has spawned countless versions of your mind pursuing different neural pathways. Right now, as you process these words, Infinite versions of your consciousness are reading this sentence while having slightly different thoughts about its meaning. But which version is the real you? In the many worlds interpretation, they all are. Every possible version of your consciousness that is consistent with quantum mechanics exists with equal reality in the infinite branching structure of the multiverse. Your sense of being a single, continuous self is an illusion created by the fact that you can only experience one branch of reality at a time. This raises disturbing questions about personal identity and free will. If every possible choice you could make plays out in parallel universes, do your decisions actually matter? Is there a version of you that made every possible sequence of life choices, experiencing every possible path through existence? Some physicists argue that this makes the many worlds interpretation scientifically meaningless. If it predicts everything that could happen will happen somewhere, then it predicts nothing specific about what we should observe. It becomes unfalsifiable in the same way that claiming anything is possible tells us nothing useful about what is probable. But supporters point out that the mathematics of quantum mechanics naturally leads to multiple realities, whether we like it or not. The mathematical formalism describes a quantum state as a superposition of all possible configurations. Measurement doesn't collapse this superposition. It simply determines which branch of the superposition we find ourselves on. Recent experiments have begun to test the boundaries of quantum superposition in larger and larger systems. In 2019, researchers at the University of Vienna demonstrated quantum superposition in molecules containing up to 25,000 atoms. Each successful test extends the size scale at which quantum effects operate, bringing us closer to understanding where classical physics emerges from quantum foundations. Yet these experiments also highlight the detection problem. Even when we can create quantum superpositions in complex systems, we can only observe one outcome at a time. The parallel realities where the experiment produced different results remain forever beyond our ability to confirm or deny. The quantum multiverse surrounds us at every moment, spawning infinite variations on every theme, creating endless alternatives to every event we experience. Yet it maintains perfect silence about its existence, revealing itself only through the mathematical necessity of quantum theory and the strange behavior of particles at the smallest scales. This is the first great barrier to multiverse detection, the fundamental isolation imposed by quantum decoherence. Even if infinite parallel realities exist just a quantum measurement away from our own, they become unreachable the moment they diverge. The very mechanism that creates multiple universes also ensures their mutual invisibility, trapping each reality in its own isolated branch of the infinite tree of possibility. But quantum mechanics is just one pathway to parallel universes. Our next chapter explores how the fundamental constants of physics might vary across different cosmic regions, creating universes with entirely different laws of nature, realities so alien that detecting them would require technologies beyond our current imagination. Chapter 3: Impossible Barriers. The barriers that separate us from other universes aren't just technological. They're rewoven into the fundamental fabric of reality itself. Detecting parallel realities might not be a problem of insufficient instruments, but rather an impossibility built into the logical structure of existence, like asking what happened before time began. To understand why multiverse detection presents such profound challenges, we need to examine what detection actually means in physics. Every measurement we make relies on some form of interaction, particles of light carrying information from distant objects to our instruments, gravitational waves propagating through space-time to reveal cosmic events, electromagnetic radiation encoding data about its source across vast distances of space and time. But parallel universes, by their very definition, exist in a state of permanent isolation from our own reality. The cosmic horizon that separates inflationary bubble universes represents an absolute boundary beyond which no information can travel. Light emitted from parallel universes can never reach us because the expansion of space itself carries them away faster than their radiation can propagate toward us. This isn't simply a matter of distance or time. Even if we waited an infinite amount of time with perfect instruments, no signal from a parallel universe could ever arrive. The mathematical structure of space-time itself prohibits such communication. It's as if other universes exist in a completely different category of reality, one that shares no causal connection with our own. Consider the analogy of a black hole's event horizon. Once something crosses the event horizon of a black hole, no information about it can escape to the outside universe. The event horizon represents a one-way boundary in space-time that permanently severs causal connections. The barriers between parallel universes function similarly, but even more absolutely. At least with black holes, information can theoretically escape through Hawking radiation over enormous time scales. Parallel universes appear to be separated by barriers that prevent any information exchange whatsoever. Theoretical physicist Max Tegmark at MIT has categorized different levels of parallel universes based on how isolated they are from our own. Level I multiverses consist of regions beyond our cosmic horizon areas of space, so far away that light from them hasn't had time to reach us since the Big Bang. These regions should have the same physical laws as our observable universe, but they're separated by pure distance. Level 2 multiverses emerge from eternal inflation, where different cosmic bubbles have different fundamental constants and physical laws. Level 3 multiverses arise from quantum mechanics, where every possible outcome of quantum events occurs in parallel realities. Level 4 multiverses encompass all mathematical structures that could possibly exist as physical realities. Each level presents increasingly absolute barriers to detection. Level I multiverses might theoretically become observable if we waited long enough for light to reach us, but the accelerating expansion of space ensures that this will never happen. Level 2 multiverses are separated by regions of inflating space-time that grow faster than any signal can cross them. Level 3 multiverses exist in orthogonal branches of quantum reality that cannot interact once they diverge. Level 4 multiverses exist as separate mathematical structures with no physical connection to our own. The quantum multiverse presents particularly puzzling barriers. Quantum decoherence ensures that once realities branch, they lose all ability to influence each other through quantum interference. But recent experiments in quantum mechanics have begun to test the boundaries of this isolation in ways that reveal just how absolute the barriers really are. Consider the quantum eraser experiments performed by researchers like Yoonho Kim at Johns Hopkins University. These experiments appear to show that quantum information can be retroactively deleted, as if the universe can change its mind about which reality becomes real. When you measure the quantum state of one particle, it instantly affects the behavior of its entangled partner, regardless of the distance between them. This quantum entanglement seems to suggest that some form of instantaneous communication occurs between quantum systems. But when physicists try to use entanglement to send actual information, they discover that the correlations appear random from either side. You can only detect the correlation by comparing measurements from both particles, which requires classical communication limited by the speed of light. This reveals something profound about the barriers between quantum realities. Even though quantum systems maintain mysterious correlations across vast distances, these correlations can't be used to transmit information. The quantum multiverse might be interconnected through entanglement, but this connection can't be exploited for communication or detection. The situation becomes even stranger when we consider the observer effect in quantum mechanics. The act of measurement appears to select which branch of reality we experience, but it provides no information about the branches we don't experience. It's as if consciousness itself creates a selection mechanism that filters one reality from infinite possibilities. while providing no access to the alternatives. Some physicists have proposed that consciousness might be the key to understanding multiverse barriers. Roger Penrose and Stuart Hameroff have suggested that consciousness involves quantum processes in neural microtubules that might be sensitive to quantum superpositions. If consciousness is fundamentally quantum mechanical, then perhaps it participates in the branching process that creates parallel realities. But even this speculative connection doesn't provide a path to multiverse detection. If consciousness selects one branch from infinite possibilities, it might be logically impossible for it to simultaneously experience multiple branches. The very mechanism that gives us consciousness might prevent us from detecting parallel versions of ourselves. The barriers become even more absolute when we consider the anthropic principle, the observation that our universe appears fine-tuned for the existence of observers. The fundamental constants of physics fall within extremely narrow ranges that allow for the formation of atoms, molecules, stars, planets, and ultimately life. If these constants varied by tiny amounts, our universe would be sterile. If infinite universes exist with different values for fundamental constants, then most of them would be unable to support observers at all. We can only find ourselves in a universe capable of producing conscious beings to observe it. This creates a selection effect that might prevent us from detecting universes with different physical laws, not because they don't exist, but because they cannot contain observers capable of detection. The anthropic principle suggests that multiverse detection might be self-limiting. Any universe we could detect would have to be capable of producing beings sophisticated enough to build detection instruments. This requirement might constrain detectable universes to have physical laws very similar to our own, making them appear like more distant regions of the same cosmic reality rather than genuinely parallel universes. These barriers aren't accidents of our current technology. They appear to be fundamental features of reality itself. The very properties that allow parallel universes to exist also ensure their mutual invisibility. It is as if the cosmos has built-in privacy protocols that prevent different realities from spying on each other. This creates a profound epistemological problem. Science depends on the ability to test theories through observation and experiment. But the multiverse theories that our best physics seems to require make predictions about realities that are fundamentally unobservable. We are forced to accept mathematical arguments about the existence of infinite worlds while acknowledging that evidence for these worlds might be logically impossible to obtain. The barriers that separate us from other universes might not be obstacles to overcome, but rather features of reality that define what detection means in the first place. Perhaps the question isn't why we can't detect other universes, but why we ever expected that we could. The very isolation that allows multiple realities to exist might make their detection a conceptual impossibility rather than a technological challenge. Our next chapter explores whether these seemingly absolute barriers might have cracked subtle effects that could provide indirect evidence for the existence of parallel realities without requiring direct communication across cosmic horizons. Chapter 4. Cosmic Echoes. While direct detection of parallel universes might be impossible, some scientists believe that other realities could leave subtle fingerprints on our own universe, cosmic echoes that whisper of infinite worlds beyond our reach. These traces wouldn't be messages from parallel Earth, but rather imprints left by the fundamental forces that govern multiple realities. The most promising evidence comes from anomalies in the cosmic microwave background radiation, the afterglow of our universe's birth. When the European Space Agency's Planck satellite created the most detailed map of this radiation in 2013, it revealed several features that don't match theoretical predictions. These anomalies are subtle temperature variations of less than 0.0001 degrees, but they hint at influences from beyond our cosmic horizon. Consider the cold spot, a region of space approximately 1 billion light-years across, where the cosmic microwave background is significantly colder than surrounding areas. Standard cosmological models predict that such large-scale temperature variations should be extremely rare. The probability of the cold spot occurring by random chance is less than 0.01%, low enough to suggest that something unusual influenced this region of space. Cosmologist Laura Mersini-Houghton at the University of North Carolina has proposed that the cold spot might be evidence of gravitational influence from a neighboring universe. In her model, our universe bubble collided with another bubble during the early stages of cosmic inflation, leaving a lasting imprint on the cosmic microwave background. The collision wouldn't destroy either universe, but it would create exactly the kind of large-scale temperature anomaly that Planck observed. If this interpretation is correct, then we're looking at direct evidence that our universe isn't alone. The cold spot becomes a scar left by contact with another reality, proof that parallel universes can influence each other under extreme conditions, even if they can't communicate directly. But the evidence remains frustratingly ambiguous. Other cosmologists have proposed alternative explanations for the cold spot, including the possibility that it is created by a supervoid, a region of space with unusually low matter density that could influence the cosmic microwave background through gravitational effects. The debate continues because the signal is right at the edge of what current instruments can measure reliably. Another potential signature comes from dark flow, a mysterious large-scale motion detected in galaxy clusters across billions of light years. Alexander Kashelinski at NASA's Goddard Space Flight Center has observed that galaxy clusters appear to be flowing toward a specific region of space at speeds of several hundred kilometers per second. This motion persists across distances so vast that it shouldn't be possible according to standard cosmological models. Dark flow suggests that some massive gravitational influence exists beyond our observable universe horizon. The most exotic explanation is that we're detecting gravitational attraction from matter in a parallel universe bubble. If our universe bubble exists near other universe bubbles in higher dimensional space, the gravitational effects of those bubbles might be detectable through their influence on galaxy cluster motions. The mathematics are compelling. If parallel universes exist as bubbles in higher dimensional space, then their gravitational effects should diminish as the inverse square of the distance through that higher dimension, not through our three-dimensional space. This could allow gravitational influences to reach across cosmic distances that would otherwise prevent any interaction. However, dark flow observations remain controversial. Some research groups have failed to reproduce Kashelinski's results, while others find evidence for the effect but disagree about its magnitude and direction. The Planck satellite data shows no clear evidence for dark flow, though supporters argue that instrumental limitations might prevent detection of such large-scale motions. Perhaps the most intriguing potential signature comes from quantum mechanics itself. If the many worlds interpretation is correct, then quantum experiments might provide indirect evidence for parallel realities through statistical analysis of quantum measurement outcomes. The idea is that while we can only observe one outcome of any quantum experiment, the distribution of outcomes across many experiments might reveal the influence of parallel realities. Physicist David Deutsch has proposed that quantum computers might serve as multiverse detectors. When a quantum computer performs calculations using superposition, it's potentially exploiting computational resources from parallel universes. The exponential speedup that quantum computers achieve for certain problems might be evidence that they're redistributing calculations across multiple realities. Consider Shor's algorithm for factoring large numbers, which forms the basis for quantum cryptography. A classical computer would require millions of years to factor a 2040 8-bit number, but a quantum computer could theoretically do it in hours. Where do the additional computational resources come from? Deutsch suggests they're borrowed from parallel universes where the quantum computer is simultaneously exploring different calculation paths. This interpretation remains highly speculative, and most quantum computing researchers explain the speed-up through purely single-universe quantum mechanics. But the possibility remains that quantum computers are inadvertently tapping into the computational power of the multiverse, providing indirect evidence for parallel realities through their enhanced capabilities. Another approach to multiverse detection focuses on cosmological constants and their apparent fine-tuning. The vacuum energy density of our universe has a value that is smaller than theoretical predictions by a factor of 10120, one of the largest discrepancies between theory and observation in all of physics. This cosmological constant problem might be explained if our observable universe exists within a larger multiverse where different regions have different vacuum energies. Steven Weinberg, Nobel laureate in physics, has argued that the observed value of the cosmological constant provides anthropic evidence for a multiverse. In most universes with different cosmological constants, either the expansion would be so rapid that matter couldn't clump into structures, or so slow that the universe would collapse before stars could form. Only universes with cosmological constants similar to our own could support the development of observers. This anthropic argument doesn't constitute direct detection, but it suggests that our universe's properties are best explained by assuming that it exists within a vast ensemble of universes with different physical parameters. The fine-tuning of fundamental constants becomes evidence for the multiverse rather than evidence for intelligent design. Some researchers have proposed more exotic detection mechanisms. Physicist Anthony Aguirre at UC Santa Cruz has suggested looking for bubble collisions in the cosmic microwave background circular patterns that would indicate our universe bubble collided with another universe bubble during cosmic inflation. Such collisions should leave distinctive signatures that future cosmic microwave background surveys might be able to detect. The key insight is that multiverse detection might not require direct communication with parallel realities. Instead, we might be able to infer their existence through gravitational effects, quantum correlations, anthropic reasoning, or collision signatures. These indirect approaches sidestep the fundamental barriers that prevent direct multiverse communication, while potentially providing evidence for parallel realities through their subtle influences on our own universe. But even these indirect signatures remain ambiguous. Each anomaly that might indicate multiverse influence can also be explained through more conventional single-universe physics. The cosmic microwave background anomalies might result from unknown astrophysical processes. Dark flow might be caused by gravitational influences from within our own universe. Quantum computational speedup might not require parallel realities to explain. This ambiguity isn't accidental. It might be a fundamental feature of multiverse evidence. If parallel universes exist in complete causal isolation from our own, then any evidence for their existence must necessarily be indirect and subtle. Strong, unambiguous signatures would violate the very isolation that allows multiple universes to coexist. We're left searching for cosmic whispers rather than cosmic shouts, looking for fingerprints rather than photographs, seeking statistical patterns rather than direct observations. The search for multiverse evidence becomes an exercise in detective work at the largest possible scales, assembling circumstantial evidence for realities that might surround us completely while remaining forever, beyond direct confirmation. Our next chapter examines the technological challenges involved in multiverse detection, the instruments and techniques that might be able to detect these subtle cosmic echoes, and the fundamental limitations that constrain how sensitive our observations can become. Chapter 5. Detection Limits. The search for multiverse evidence pushes our instruments to their absolute limits, revealing fundamental constraints on how precisely we can measure the cosmos. Every potential signature of parallel realities exists right at the edge of detectability, forcing scientists to confront the ultimate boundaries of observational science. Consider the sensitivity required to detect cosmic microwave background anomalies that might indicate universe collisions. The temperature differences we were looking for are approximately 0.000 Kelvin variations so small that they represent energy differences of less than 1/1000th of an electron volt. Detecting such subtle signals requires instruments that can distinguish temperature variations smaller than the quantum fluctuations of electromagnetic radiation itself. The Planck satellite, launched in 2009, achieved temperature sensitivity of 2 microkelvin across the entire sky. This represents one of the most precise measurements ever made in astronomy, requiring detectors cooled to 0.1 Kelvin and shielded from every possible source of interference. Yet even this extraordinary precision might not be sufficient to definitively identify multiverse signatures among the noise of quantum fluctuations and instrumental uncertainties. Next-generation cosmic microwave background missions like LIGHT-BIRD and CMBS-4 promise even greater sensitivity, potentially reaching temperature precision of 1 microkelvin. But each improvement in sensitivity reveals new sources of systematic error that must be understood and controlled. Solar wind particles, interstellar dust, gravitational lensing by dark matter, and even the motion of our galaxy through space all create signals that can mimic or obscure potential multiverse signatures. The fundamental problem is that multiverse evidence, if it exists, consists of extremely subtle statistical patterns buried within cosmic noise. Distinguishing real signals from random fluctuations requires enormous datasets and sophisticated statistical analysis techniques that push the boundaries of what is computationally feasible. Gravitational wave detectors face similar challenges when searching for signatures of parallel realities. Theoretical calculations suggest that gravitational influences from neighboring universe bubbles should create correlation patterns in gravitational wave signals across different detector locations. But these correlations would be incredibly weak, perhaps detectable only through statistical analysis of thousands of gravitational wave events collected over decades of observation. The Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030s, will observe gravitational waves from space with unprecedented sensitivity across different frequency ranges. LIS ACE-3 spacecraft, separated by 2.5 million kilometers, will form a giant triangle capable of detecting gravitational waves with wavelengths comparable to the size of the solar system. But even LIS's remarkable sensitivity might not be sufficient to detect multiverse signatures. The gravitational effects of parallel universes, if they exist, would be redshifted and diluted by the expansion of space, making them extraordinarily difficult to distinguish from astrophysical gravitational wave sources within our own universe. Quantum multiverse detection presents different but equally challenging technical requirements. If parallel realities influence quantum measurement outcomes through subtle correlations, detecting these correlations would require quantum experiments with unprecedented precision and scale. Current quantum computers operate with error rates around 0.1% per quantum gate operation, but detecting multiverse correlations might require error rates 1,000 times smaller. The problem isn't just technical precision, it's also statistical power. Quantum correlations that might indicate parallel reality influence would be incredibly subtle, perhaps detectable only through analysis of millions or billions of quantum measurements. Such large-scale quantum experiments would require quantum computers far more sophisticated than current technology can produce. Moreover, quantum decoherence ensures that any correlations between parallel realities decay extremely rapidly. Detecting multiverse influences on quantum systems would require measurements performed faster than decoherence times, typically less than microseconds for systems large enough to produce detectable signals. This creates a fundamental trade-off between signal strength and measurement speed that might make quantum multiverse detection impossible in principle. Particle physics experiments offer another potential avenue for multiverse detection. but they face their own daunting technical challenges. If parallel universes exist with slightly different fundamental constants, they might leave signatures in high-energy particle interactions through virtual particle exchanges or quantum field fluctuations. The Large Hadron Collider, LHC, at CERN accelerates protons to energies of 6.5 teraelectron-volts, creating conditions that haven't existed since the first fraction of a second after the Big Bang. These extreme conditions might be sensitive to influences from parallel realities, but detecting such effects would require measuring particle interaction probabilities with precision far beyond current capabilities. Future particle accelerators, like the proposed International Linear Collider or Circular Electron-Positron Collider, could achieve even higher energies and precision, but the technical challenges are enormous. Each improvement in collision energy requires exponentially more powerful accelerating systems, while each improvement in measurement precision demands correspondingly more sophisticated detector arrays and data analysis techniques. The fundamental limit might not be technological, but rather theoretical. Many multiverse detection schemes rely on statistical analysis of large datasets to identify subtle patterns that might indicate parallel reality influences. But distinguishing genuine multiverse signatures from random statistical fluctuations becomes exponentially more difficult as the signals become weaker. Consider the multiple comparison problem that plagues all searches for rare phenomena. When you analyze thousands of potential multiverse signatures across millions of data points, you're virtually guaranteed to find some patterns that appear statistically significant purely by chance. Correcting for these false positives requires statistical techniques that become increasingly conservative as the number of tests increases. The result is a catch-22. Genuine multiverse signatures are expected to be extremely subtle, but subtle signals are exactly what's most difficult to distinguish from statistical noise. As detection sensitivity improves, the number of potential false signals increases, making it harder rather than easier to identify real multiverse evidence. Some researchers have proposed that machine learning techniques might help solve this problem by identifying complex patterns in cosmic data that human analysts might miss. Artificial neural networks trained on simulated multiverse signatures could potentially recognize subtle correlations that indicate parallel reality influences. But machine learning approaches introduce their own limitations. Neural networks are notoriously difficult to interpret, making it hard to understand why they identify particular patterns as significant. Moreover, training neural networks to recognize multiverse signatures requires accurate theoretical models of what those signatures should look like, models that remain highly speculative given our limited understanding of multiverse physics. The detection limits we face aren't just temporary constraints imposed by current technology. They represent fundamental boundaries imposed by quantum mechanics, general relativity, and information theory. The very nature of parallel realities, their causal isolation from our own universe, might make their detection a logical impossibility rather than a technical challenge. We're reapproaching asymptotic limits, where each improvement in instrumental sensitivity yields diminishing returns in terms of new physical insights. The cosmic microwave background has been mapped with exquisite precision. Gravitational waves are detected routinely, and quantum systems are manipulated with ever-increasing control. Yet multiverse evidence remains tantalizingly just beyond our grasp, suggesting that the barriers to detection might be more fundamental than we initially imagined. Our next chapter explores whether theoretical advances in physics might provide new approaches to multiverse detection, ways of thinking about parallel realities that could reveal detection strategies currently beyond our imagination.